The overall goal of this procedure is to fabricate a multiplexed microneedle-based sensor for transdermal electrochemical detection of various target analytes that can be simultaneously measured. The first step is to fabricate hollow microneedle arrays using microstereolithography and create electrode array cavities using laser micromachining. Then prepare the individual carbon pastes and fill the electrode array cavities. Next, calibrate each of the carbon pastes over a range of physiologically relevant concentrations. Ultimately, a transdermal in vivo electrochemical device is created that is capable of simultaneously measuring multiple analytes in complex physiological microenvironments for a range of biomedical applications.
The main advantage of this technique over existing methods is the ability to perform multiplex sensing in a minimally invasive manner.
This device can be utilized as a research tool to measure acute medical responses, gain understanding of adaptations during physical exercise, and monitor illnesses that affect the skin. The implications of this in vivo microneedle sensor extend towards diagnosis of skin tumors, because tumor microenvironments can serve as indicators of tumor proliferation and metastasis.
Our goal with this device is to use microneedle arrays as a minimally invasive mechanism to access dermal interstitial fluid floor electrochemical analysis.
Begin in the three-dimensional modeling software SolidWorks and design a pyramidal-shaped hollow microneedle array. Then, using the Magics RP13 software, design a support structure that provides a base on which the microneedles are built. Next, control the fabrication process using the Perfactory RP software. Upload both the linked support and the microneedle array files. Then select the number of microneedle arrays to be fabricated and determine the placement of devices on the fabrication plate. In the Perfactory Rapid Prototyping Manufacturing System, select Ultraviolet mode at 100 milliwatts and perform the calibration procedure. Verify the deviation in the energy is within plus or minus 2 milliwatts. Once fabrication of the microneedle array is complete, remove the microneedle array from the base plate. Develop in isopropanol for 15 minutes. Then dry the arrays with compressed air. To ensure complete polymerization, cure the microneedles at room temperature for 50 seconds. Examine the microneedles via light microscopy. Verify that each fully fabricated microneedle bore is hollow and unobstructed. Expose the underlying individually addressable connecting copper wires in a flat, flexible cable. Create patterns for the laser ablation and send these patterns to the laser system. Now position the cables in a jig to properly align them on the laser ablation plate. With the rastering approach, create 500 micrometer diameter cavities in the insulating portion of the flexible cable. Clean the modified flat flexible cables with an airbrush that sprays acetone at 40 psi. Then rinse with isopropanol and deionized water. Using a light microscope, verify that no insulating film remains over the exposed copper strips. The next step is to create a holding cavity for the carbon pastes. Ablate Melanex tape containing a single-sided, pressure-sensitive acrylic adhesive in the pattern previously used for electrode strips. Now orient the tape over the ablated electrode strips. Compress the tape to ensure a proper connection. Then ablate double-sided Melanex tape and align the tape to enable bonding between the microneedle arrays and the carbon paste electrode arrays. Mix 10 milligrams of glucose oxidase and 2.2 milligrams of polyethylenamine into a homogeneous glucose-sensitive carbon paste. Then add 60 milligrams of rhodium on carbon powder and mix in 40 milligrams of mineral oil. Store the paste at 4 degrees Celsius. For the pH-sensitive carbon paste, mix 30% mineral oil and 70% graphite powder. Using a thin piece of plastic as a trowel, pack the paste into the electrode cavity until a smooth surface is achieved. Repeat with a second clean weighing boat until the excess paste is removed. Then wash with deionized water. Next, place a 20 microliter drop of freshly prepared fast blue solution over the packed paste electrode. After a 30-minute incubation period, rinse with deionized water. For the lactate-sensitive carbon paste, combine 2.5 milligrams of rhodium on carbon powder with 2.5 milligrams of lactate oxidase. Alternate between 5 minutes of sonication and 5 minutes of vortexing for 5 rotations. Proceed to pack the paste into the electrode cavity. Finally, rinse with deionized water. To detect lactate, measure the chronoamperometric response of the sensor and record the current after 15 seconds. To detect glucose, measure the chronoamperometric response of the sensor. To create the calibration curves for lactate and glucose sensors, successively add the respective analyte prior to chronoamperometric measurements. Alternatively, perform fixed potential chronoamperometric measurements. While stirring, allow sufficient time in between each analyte addition for current stabilization. To monitor the pH, perform cyclic voltammetric scans and record the positions of the oxidative peak potential values. Create pH calibration curves by measuring the position of the oxidative peak potential in recorded cyclic voltammograms over a series of known pH values. The process of constructing a multiplexed microneedle-based sensor starts with designing the microneedle array in SOLIDWORKS and then designing the support structures in Magix RP13. These scanning electron micrographs show a microneedle array and a single microneedle within this array. The sensing platform of the microneedle-based sensor is created by using laser ablation to create the electrode arrays in the flat, flexible cable, and subsequently filling these arrays with carbon paste. The electrocatalytic reactions for glucose and lactate are presented along with the operating parameters for detection. This typical calibration of lactate-sensitive paste with 15-second chronoamperometric scans shows each increase in current corresponding to a 2 millimolar addition of lactate. A single continuous chronoamperometric scan is used while monitoring glucose. Calibration of the sensor is done by spiking in concentrations of glucose and then allowing the current to stabilize. This schematic shows the electrocatalytic reactions for detection of acidity. Here, cyclic voltammograms at the pH-sensitive microneedle in 0.1 molar phosphate buffer are shown over 4 different solutions with pH values ranging from 5 to 8 in 1 unit increments. Since the oxidative peak potential shifts with increasing pH values, this phenomenon is used as an indicator of the pH value.
Once mastered, this device can be fabricated properly in 2 days.
When attempting this procedure, it is important to note that the various carbon pastes will not retain their selectivity if mixed with one another.
Following this procedure, additional selective carbon paste can be added to the electrode array in order to monitor other analytes in the skin.
The development of this device could pave the way for researchers in the field of wearable sensors to perform medical diagnosis and explore fundamental biomedical science questions.